Hello there and welcome to week 5 now of this module. So we're almost at the midway point for this term and we're carrying on with the final bit of ordinary differential equations. The main thing we're focusing on today is deriving the Runge-Kutta method. You may have seen it written down in the past, this multiple evaluation of functions to get your time integration. But here we get right into the nitty-gritty about how it's derived into Taylor series. Okay, so I'm now going to hand over the board. Working on them. So last time we had this formula for the Runge-Kutta second order. That the new value xn plus 1 equals x of n plus delta t times ck1 plus dk2, and k1 was simply the function at your start of your interval, and k2 was somewhere within your time step like this. So the key point with the Runge-Kutta is you're evaluating the function within the time step. Okay, we're going to do the other type of method that we're going to look at later is going to involve values actually on the time steps, but this is within the time step. And we set the problem up with these undetermined constants, little a, little b, little c, and little d. Okay, so we set up this method. And we're told that it's second order. Well, we need to show you with terms of Taylor series. So we're going to determine these constants a, b, c, d by Taylor series. If I call this the method, the numerical method. So we're going to do two Taylor series. The first one is going to be of the method, and the second one is going to be of the true solution. And then we can compare the two Taylor series, and this will give a constraint on little a, little b, and little c, and little d. So I describe this as a fairly long-winded way of deriving Runge-Kutta second order, but it's the one that gives us flexibility of designing more than one method. After we've done the long-winded way, I want to show you a quick way of deriving one form of the Runge-Kutta that may be a little bit more intuitive. So we got this. So we've got these ingredients: little a, little b, little c, and little d, and we have these two Taylor series. So let's do the first Taylor series. So the Taylor series of the method, if you like. And here we expand this function in the definition of k2, x of n plus a delta t, k1, comma t of m plus b and delta t, to order delta t squared, or in other words, remainder of order delta t cubed. Let's just do that. So that means that xn plus 1 then equals x of n plus delta t. So this is just doing your Taylor series. C plus f plus d times f xn plus a. We haven't done the expansion yet. So that d is little d. And to expand this thing, this xn, sorry, a little bit clearer there. We're going to use a second order, a 2D Taylor series. So we're going to use a 2D Taylor series, which is very similar to what you did in calculus at the end of last year series. So we've been doing 1D so far in our numerics, but with this place we're going to allow for things to be a function of x and t, and that simply is f plus partial f by dx times delta x plus partial f by dt delta t plus other terms. Actually, it turns out we're going to only need this first order expansion of f plus delta x and t because we've got another delta t here, so it's going to be order delta t squared when we multiply it through. So but the point is that you have the partial f by dx for the variation in x, the partial f by dt, the variation in t. So you put that together, then we have that xn plus 1 equals xn plus all this stuff, delta t times c of f plus d of f plus dA delta t f partial f by dx plus dB delta t partial f by dt. And remember, these partial derivatives come from a first ordered expansion, but we're multiplying it through by delta t, so this is actually up to delta t squared. So it turns out that the remainder term that we're not showing is of order delta t cubed. So this is actually a second order approximate scheme. Reason being is that when we bring xn over to the left hand side and we divide through by delta t, that's delta t cubed term is going to be at order delta t squared. So this is going to get this. So this will give a second order scheme because we're dividing through by delta t in this delta t term. So that's good. That shows we've got this accuracy coming up. Let me just simplify this a little bit. Oop. It's xn plus 1 equals x of n plus, okay, so I'm just going to factorize various things, c plus d delta t of f, so that's the first order term in delta t, and then the second order term in delta t is this one. Okay, so you've got the first order term and then you have the second order term. Okay. Right. So we're going to just pause with that Taylor series. So this is our first order Taylor series. So it's order delta t cubed. So this is our Taylor series 1, should we call it, or the Taylor series of the method. And at the moment we have these constants c plus d, a and b undetermined, unconstrained. Okay, so that's the first bit we do. We do this Taylor series, and because it's up to delta t cubed, we can clarify that actually what this method is going to give us is a second order scheme. So it's suffice to say, if you want to derive a even higher order Runge-Kutta, you do even a higher Taylor series, and the algebra gets more involved. The algebra turns out to be very, very involved actually for, say, fourth order, and we don't do it in this module. We just give you the result. There are papers out there where they actually go through each of the steps, but it's really the principles are exactly the same. Okay, so that's a Taylor series 1, and Taylor series 2 is of the true solution, I call it. What do I mean by that? Well, if we expand the true solution using Taylor series just in time, we get this. Xn plus 1 equals x of n plus delta t times x dot, which obviously is dx by dt, plus delta t squared on 2 x double dot plus order delta t cubed. So this is a Taylor series which is kind of looking similar to the one we had last. It explicitly got terms in delta t times delta t squared, and then we have all this stuff left over. So we're on the point, but at the moment we don't know what x dot and x double dot is. So we take x dot and x double dot from the ODE. So that's why I call it of the true solution, because we're using the ODE. So the ODE we're using is x dot is right hand side f of x and t. So I'm writing the right hand side now in terms of x and t, the most general form of this ODE. And then again use your sort of your chain rule, partial derivatives. So the chain rule to get x double dot, that's a second derivative. Remember, x dot is simply dx by dt, right? X double dot is the second derivative. Is d by dt, big D by dt of f of x comma t. And again, we use a rule very similar to your the one we use with the 2D Taylor series. Remember that, so d by dt is the absolute derivative, if you like, with respect to time. But of course, f depends on x and t. So we actually have variation of f with x times dx by dt plus df by dt. And of course, dx by dt is simply x dot, yeah? So let's just write some of those things again. I'm conscious this is quite involved today, but we're reaching half term and we're on a year 2 module, so we've got to get things a little bit harder. So plus delta t squared on 2 x double dot. We know that x dot is simply f. I'm just going to drop the x comma t for, and we know that x double dot is partial f by dx, x dot plus partial f by dt. So we basically just substitute these two expressions 2 into 1, and then we get an expression that looks quite a lot like our original Taylor series. F delta t squared on 2 partial f by dx. And here I appreciate that x dot, right? X dot is just f. So I can put f in here and partial f by dt. And let's put the order just up here, order delta t cubed. Okay, find a nice big whiteboard, I could just fit it in really easily. Okay, so there's you up, there you are. Okay, so that's the ODE Taylor series. And then if we just write down from before, and the Taylor series 1, if you like, we now have it exactly same form. So xn plus 1 equals x of n plus c plus d delta t on f, and then we have plus d delta t squared little a partial f by dx f plus b delta f by dt. So we now have these two Taylor series. Let's just see where we've gone. So we've got this Taylor series that comes from the ordinary differential equation itself without any coefficients, and then we've got this method that we've written down in terms of coefficients, little a, little b, c, and d, and we've written by Taylor series we've written it in exactly the same form. So whilst we're not going to pinpoint exactly values for a, b, and c, and d because we've just got two equations, we can now constrain them quite nicely, and that helps us form the different Runge-Kutta methods. So it turns out there's more than one Runge-Kutta method depending on how you set up these coefficients, little a, b, and c, and d, and we're going to just mention the two most common ones. So here we can see that c plus d is going to equal 1, right? That little d, little d times a, is going to be a half to fit in here, and little d times b is also going to be in half. Okay, so that's the idea. So just keep an eye on the time there. I try to use the whole screen for this stuff so I get as much forward. So comparing Taylor series 1 and 2. Gives the following. So c plus d equals 1. And dA, let's write that a little bit clearer, dA equals dB equals a half. So what we've got there is three equations, right, for a, b, and c, and d. So we have three equations, four unknowns. So we have to make a choice about one of those constants. So we have to choose, have to specify one of a to d, and then the rest will follow by these relationships. Okay, so and this is where the different schemes come in. So this the most common one is called the standard RK2. So RK stands for Runge-Kutta, 2 stands for second order. So we know it's second order because of the Taylor series we're using. That's a really helpful thing about deriving it, is we see that this second order accuracy is built into the method. Yeah, so the RK2, or sometimes called Hoynes scheme, is that C equals D equals a half. So if you choose C to be a half, then D's got to be a half, and then DA is a half, so that means A is 1 and B is 1. Okay. And let's just write that, substitute that into the method. So we substitute those values into the RK2 method. We then have that K1 is f of x of n comma t of n. Then we have K of 2, but we now have the constant, so that's f evaluated x of n plus delta t K1, and then t of n plus delta t. And then putting it together implies xn plus 1 equals x of n plus delta t onto K1 plus K2. And this is the most common form, and we can see what we're doing if we just look on the timeline. We're evaluating f of x of n comma t of n at one point, and then you've got t plus delta t, and then K2 is attempt to try and find the function kind of at the other end. So k2 is a value function k1, and by averaging the two together we get the new value. Now it's interesting to see if we just really simplified this massively, i.e. we undid the algebra we've done, but just see what we've done. If k2 was 0, if we didn't have k2 at all, or if k2 is equal to k1, say, we'd recover xn plus 1 equals xn plus delta t times k1, which is just your forward Euler method. So this really nice thing about the derivation of Runge-Kutta is that you can see very clearly where you start with forward Euler, and you can see by adding this extra term in there how we're getting that extra accuracy. How about having multiple evaluations of f? Okay, so I think that's probably enough information for one video, and I'll carry on with this discussion of different Runge-Kutta methods next video. Okay, see you later. I'm going to take that off there, and I'm going to stop.